I'm Cindy Kelly, Atomic Heritage Foundation, and it is Wednesday, February 22nd, 2017. I'm in Encino, California. Maybe the first thing to do is say your name and spell it for us.
Okay. It's William Seaman, Seaman, Ginell, Ginell.
Great. Well, why don't you start at the beginning? Tell us when you were born and where, and a little bit about your childhood.
Okay. I was born in actually New York City, although my parents at the time lived in New Jersey, in Lakewood, New Jersey. My mother went to the hospital in Manhattan, where I was born, in August 1923. My parents operated a let me think about it. It was a rooming house, actually, in Lakewood. After that, they moved to New York City, where my father operated a restaurant. My parents worked in the clothing industry for a while. Things were pretty difficult. They came to this country from Russia in the early 1900s, and they were married in 1911. My brother Robert was born in 1912. So there's an important difference in age between my brother and myself. He acted more like my father than my brother. And my career is pretty much a function of my relationship with my brother. He was a chemist who worked in Macy's during the early 1930s and went to school at night at Brooklyn Polytechnic Institute. And he finally got his bachelor's degree in 1936. He influenced me in being a chemist. Let's see, I went to high school in Brooklyn. We finally moved to Brooklyn. And I was interested in science in those days. I was captain of the chemistry squad in high school, and the squad's duties were to prepare the experiments for the demonstrators. I was head of the physics squad, where I did the same thing. So all of these activities were after-school voluntary things. We had a chemistry club in high school, and we were very active. During the, when was it? I was in high school in the late 30s, and Westinghouse sponsored a group of science clubs throughout New York City, and they had exhibits at the Natural History Museum in New York, and I had several exhibits there, and I was very happy. When I graduated in 1939, I applied to Brooklyn Poly for admission. I was rejected. My brother was there. He was on the staff in the chemistry department. They had a limitation on the number of Jews that they admitted, which they didn't advertise the fact, and I was outside of this range. Well, my brother was very unhappy about this. He spoke with the head of the chemistry department, Professor Raymond Eller Kirk, and he was very disturbed. He went to management at the university and got it reversed. So I was admitted in the fall of 1940. I graduated from high school in December of 1939, and I wasn't admitted to Brooklyn Poly until September of 1940. Well, in the interim, I worked for my father, who worked on monuments, tombstones. And I helped prepare the tombstones, learned a lot about handling granite and doing the inscriptions and things of that sort. In the summertime, I operated a parking lot across the street from a cemetery and made a few extra dollars. We sold soda also, and I shared this with a cousin of mine who was about my age. Well, I went through Brooklyn Poly, 1940, graduated in December of 1943 with a Bachelor of Science in Chemistry. While at Poly, I worked for the National Youth Administration in the chemistry department stockroom. I was responsible for taking care of the scientific instruments that were used in the lectures. I worked in the chemistry stockroom. Also, during the summer of 1942, I worked in a hospital in Brooklyn doing chemical analysis of blood. I was the first undergraduate that they had ever hired. I was doing cholesterol analyses, blood clotting times, very important analyses, and everything worked out fine. We had a very forward-looking director of the laboratories. He was a friend of my brother's. That's how I got the job. Well, in 1939, one of the courses that I took as a senior was a course in atomic physics, which was being given by a brand new PhD in physics from, I guess it was an Oregon university. And he was telling us all about fission, which had just been discovered, all about the neutrons. And I remember very distinctly his saying that he would be willing to bet that 95% of the physicists in America were working on nuclear energy. He wasn't on the project at all. He had no way of knowing specifically what was going on, but his predictions were very accurate. Well, in December of 39, the Army was sending interviewers around looking for people for the project, I learned later. So I was interviewed, and he told me about something about the job. He couldn't tell me what it was, or where it was, or anything about it. If I accepted it, it had to be blindfolded. Well, I accepted. And about 2 weeks afterward, he said that the FBI had investigated me, and I passed, and so I was accepted for the SAM laboratories at Columbia. To back up a little bit, I had a deferment from the draft because I was a student between 1940 and 1940 and 1943. When I was a sophomore, they were talking about drafting us. And they said, well, why don't you apply to the Navy, to the V-12 program? They would allow you to complete your education, And then after you graduated and got your degree, you'd be sent to officer candidate school. So a lot of my classmates took that up. I went through the examination in downtown Manhattan and failed. I was red-green colorblind. I couldn't make out the numbers in this book. So they turned me down. And then I got a further deferment from the draft board that allowed me to complete my degree. To work for SAM Labs in December of 1943. Yes. And I was assigned, or I was told, to go to the Pupin building at Columbia University. Pupin was the physics laboratory. And I reported to their very strict security and was taken up to the 10th floor and introduced to the director of the laboratory that I'd be working in. His name was Francis T. Miles, actually, who was running, I found out later, a set of tests that were vital for characterizing the gaseous diffusion project. At that time, the barriers for separating the uranium isotopes had not been fixed as yet. They were trying all kinds of porous materials that could be used to separate the U-235 from U-238 by gaseous diffusion. The problem was that, one of the problems, was that the gas they were using was uranium hexafluoride, which is a gas at fairly low temperatures. And this was extremely corrosive. And there were very few materials that could withstand the corrosive action of fluorine and fluorides. And part of our job was to determine what would happen if, what would be the result of tests involving various experimental barrier materials that were being made at a different location at Columbia. These were small samples that were prepared in different ways. And the problems were that corrosion of the barrier material by the uranium hexafluoride would change the pore sizes and the pore size distribution and could plug up the barrier completely with insoluble uranium compounds, which could be lost. So the ideal barrier material was one that would resist fluorine, resist uranium hexafluoride, and maintain its properties over a long period of time. So we had an experimental group of boxes, we called them, in which we circulated uranium hexafluoride gas through the barrier and periodically measured the porosity of this barrier material and how it changed with time. This information was very important for the design of the main plant at Oak Ridge, Tennessee, that was designed and being built at that time. So there was a very small group at the Schermerhorn laboratories at Columbia. SAM had two designations, and I'm never sure which one is correct, either special alloy materials or substitute alloy materials. And I don't know which one is correct. actually, uranium was never used at all. It was called tuballoy. And this was the name given by the English workers who were also studying gaseous diffusion. They called it tuballoy hexafluoride. Well, I remember going to the library at Columbia to look up the properties of uranium hexafluoride, and the volume was missing, which was a dead giveaway as to what was going on. And uranium hexafluoride is the only volatile compound at low temperatures, so there was no choice. It was fortunate that fluorine only had one isotope, so there weren't a lot of different UF6s depending on the molecular weight of the compound. There were only two. So we measured the porosity in this equipment, and it was a very interesting way to go. We had a canister of UF6, and we heated it up in a chamber that was warmed up by light bulbs. And the temperature was controlled so that the uranium fluoride gas was generated, and it was sent through a system of copper tubes through the barrier material, which was in the form of a disc. And at the other end of the line was another container cooled with dry ice. And dry ice, the heat transfer from dry ice into other items was very slow, so they added trichloroethylene, which is cleaning fluid that used to be used in dry cleaning. It's now forbidden. It's a carcinogen. And so our laboratory always smelled of trichloroethylene. And I'll get to this in a minute. So what we did was to measure the flow from the hot source through the barrier to the cold sink where it was condensed. And then when all the UF6 had been transferred, we reversed the flow again by a series of valves so that what was previously the hot sink was now the cold sink was now the hot sink. So we always had the flow going through the barrier in the same direction. And periodically, we had to measure the properties of the barrier material. And this was done by determining the time required for a given quantity of gas to pass through the barrier under given cold and hot sink conditions. And this involved a glass pressure system, which I built. I was blowing glass at the time. I'll get to that in a minute. And there was an automatic system that as soon as the gas pressure reached a certain value, it would turn a stop clock on. And when the pressure diminished to a certain point, it would turn it off, so that we had a fixed measure of the time it took for a given quantity of gas to go through the barrier. And this was a function of the porosity of the barrier. So we tested a lot of samples and got a lot of data. The data analysis was done by Frank Miles and his assistant, and what the disposition of that data, I don't know. It was all really classified information. The whole project, of course, was classified. This was a 24-hour system. We had about 10 boxes in which this was going on, and we had about 4 operators on each system operating 24 hours a day. So we worked shift work. Most of the people on shift work were civilians, although after a little while we got some Army people in, and that was a problem. It was not generally known or advertised that the Army was in this project at all. It was SAM laboratories, and that was it. So that those who were in the Army and assigned to this laboratory could not wear their uniforms to work. They had to wear civilian clothes. The Army did not provide civilian clothes. So there was a lot of unhappiness, and eventually the Army relented and put everybody back into uniform. Now at that point, I was a civilian for about a year working in this laboratory, and then the draft board decided they could no longer give me a deferment, even though they didn't know what we were doing. I was working at a university. And so I got my draft notice. When I informed the SAM Army people about this, they said, okay, get drafted. When you get your serial number, tell us where you are and the serial number. And that's what eventually happened. But meanwhile, while I was afterwards, while I came back from the Army, I was walking around my home, where I lived at home, and was receiving rations and quarters, but I couldn't wear my uniform. Well, the people in my neighborhood complained to the draft board. Here I was out of uniform and in uniform. And they notified the Army, and the Army said, mind your own damn business. And that was it. So eventually I got to wear my uniform all the time. Okay, so I was drafted. I was drafted at Fort Dix, New Jersey. This was in December of 1904. Yeah. Yes. I remember distinctly it was around Christmas time, and the PA system was playing Bing Crosby singing Don't Fence Me In, which hit home at the time. So I finally got my shipping orders from Fort Dix, and it was to an engineer training camp in Louisiana, Camp Claiborne. So I packed up all my stuff, got on the train to go to Louisiana. Well, the train entered Little Rock, Arkansas, and I had to change trains at that point. Somebody directed me to the wrong train. And I was off, I don't know where, but I was on the wrong train. The conductor said, okay, we'll let you off at the first stop, which was out in the wilds of Arkansas. I got out with my duffel bag in uniform, a buck private, and tried to get back to Little Rock. Well, it took me a little while. I hitched, I thumbed a ride, and I got back to Little Rock, finally found the right train, and got to Alexandria, Virginia, which is near Camp Claiborne, and was met by a delegation from the camp. They were meeting all the trains at that point. So I got into Camp Claiborne and was assigned to a company of new engineers. This was an engineer training camp. When they said engineers, they meant engineers. The people in my company were bulldozer operators, tractor operators, construction people. They were engineers. And here I was, a young college kid, and this was noted by the first sergeant, who didn't particularly care for, who's regular Army, didn't care for young college kids. So I got KP very often. Well, I was there doing basic training for a little over a month. And then I finally got called into his office. And he said, "You're being transferred to Manhattan. How the hell did you manage to do that?" I don't know. I knew nothing about that. So I packed up my stuff and got back on the train, reported back to my same job at SAM Labs. Well, by that time, the laboratory at Columbia had closed down. They had finalized the design of the barrier materials, and these were being produced at various places in the United States, some up at Tonawanda, upstate New York, by Hudai Hershey, others by Kellex in New Jersey, being made all the time. And I found out later that these were tubular elements, but all information about the nature of the barrier was completely secret. Nothing was omitted. Well, by this time, they had transferred me to the Nash Building. The Nash Building was a large commercial structure on the outskirts of Upper Manhattan. I worked there for a couple of months. I don't remember what I was doing. But I do remember at this time that my girlfriend called me and told me that Roosevelt had just died. So this was April 12th, 45. I remember that. And shortly thereafter, I got my shipping orders to Oak Ridge. Well, Oak Ridge was another story. Dogpatch, we called it. Dogpatch was the name of the town where Little Abner resided in the cartoon strip. And there were stories about the knee-deep mud and the wooden sidewalks in the downtown area, and by George, they were right. So I was put up in a barracks, which was a very long building with double-decker bunks and no privacy, a communal bathroom with no privacy again. And this is where all the GIs were kept. This was Barracks E in Oak Ridge, and you'll probably find a lot of designations to Barracks E. But we had a very interesting time. It turned out that most of the people in the Army had technical degrees. The Army had searched through their rosters and pulled out people from all over the country who were in the Army who had any kind of technical training. And so I would estimate that at least 2/3 to 3/4 of the people had degrees in science or engineering. And the living conditions were pretty severe. This long barracks building was heated by a wood stove in the middle, and that was unsatisfactory. Eventually, they moved us to 2-story buildings that had been built for the construction crews who built Oak Ridge. And the construction was completed, so these people had been moved out. These were empty. So they moved the SED into those buildings. And I was in Barracks Lafayette. The interesting part about it was that either you had a separate room with a door, or there were two of you to a room. I had a roommate. His name was Ed Quinn. He was working for in the same area that I was, and we hit it off very well together. These barracks were more in the nature of a university hall, living hall. We had pool tables and ping pong tables. There was a dark room, a piano, facilities for cooking if you wanted it. It was a communal relaxation area. It was like being at a university. So we'd go to work every day, and weekends we could get a weekend pass most of the time. So we did a lot of traveling around the South, very often like this, thumbing our way. A good friend of mine had a car, and we went all over in his car. He also had a Leica camera, which I envied very much. I had a little toy camera, took some pictures. We visited many of the dams in the Tennessee Valley. Went all over the South. We were out just about every weekend. There are a lot of activities at in these areas, and these are shown in the yearbook that was issued. There were sports teams, there were play productions, you name it. It was a university environment. We had fun. The work that I was doing in the laboratories, I was assigned to K25, which is the main gaseous diffusion plant. And I was doing some sort of work on the analysis of the corrosion process, the kinetics of corrosion of materials, how they withstood fluorine and UF6. Let me go back a little bit and bring up the fluorine problem. UF6 could only be handled in metallic systems. It attacked glass. So, and it had to be done in vacuum and away from water. So this called for metal systems. Well, copper was fine. There was a lot of background information on copper systems that were being used for refrigeration. Making joints, valves that were suitable. And so all of our systems were copper. But if you added uranium hexafluoride to bare copper, it would react, produce an insoluble uranium compound that deposited on the surface, UF4, and you'd lose the uranium. So this copper had to be passivated, and it was passivated by being treated with elemental fluorine. We had a tank of elemental fluorine supplied by DuPont. Remember, it was a big copper tank, and it was very dangerous to handle. Fluorine, when exposed to air, bursts into flame, produces all kinds of toxic products, among which are hydrogen fluoride, HF, And actually, all the windows at SAM labs where we worked were frosted over because of the etching by the hydrofluoric acid in the air. Why none of us got sick, I don't know, but it was very toxic. And the fumes of the trichloroethylene are also very toxic. I don't remember ever having a visit by health physics. And I'm sure there must have been a health physics facility at SAM. Now, it turned out that many of the activities in pupine were on the 7th floor. And I found out later by reading the Smythe report that they had tons and tons of uranium there. And they were measuring the separation factor through the barriers. They were measuring all kinds of other materials. I think they even had some pile-related activities going on. But I knew nothing of this at that time. We were strictly compartmentalized, and it worked. Let's see, what else? I think there were about 4 GIs in our group at SAM Labs. One of them was a good friend of mine named Carl Strick, and I often wonder what happened to him. He was a sergeant in the regular army, and I don't know what his technical background was, but he was working shift work with the rest of us. What else? Yeah, we had some practical jokers in the group. One night on shift work, we went down to Morningside Park, which was outside of the laboratory, and picked up a rock about that big, put it on a little trailer, and brought it in and put it on the desk of the supervisor, whom we didn't like, who came in the morning and was astonished. He was very unhappy. And this same guy who perpetrated this activity was known to drop balloons filled with water outside the window, and he did all kinds of things. I wonder what happened to him. Let's see, what else? I guess that's
So
the highlights.
Were you in Oak Ridge when the atomic bomb was dropped on Hiroshima?
Yes.
Tell us
Yes.
about
We knew about that beforehand, before it happened. Some of the guys worked in the castle, which was the administration branch of the SED, and they were preparing a press release to be distributed the next day. We got a copy of that the previous day, so we knew what was going to happen. And we weren't really surprised. There were many discussions as to should we have done this or not. And this decision is still being argued throughout the technical community and the legal community. And I think the major opinion at that time was that it was worthwhile. We had saved a lot of lives that would have been lost during the invasion of Japan. And it was a matter of balancing one way of operation and another. Life in Oak Ridge was interesting. I had some friends who were married and lived in one of the houses downtown. And I ran into him later at Brookhaven National Laboratory, where I worked. And first time I was on a horse was one weekend, and we went out riding, and they gave me a horse named Billy. They didn't tell me about this horse. While I was sitting there very calmly, somebody slapped the horse on the rump, and he took off. He was a jumper, and I didn't know this. Fortunately, we didn't run into any fences where he had to jump. I was scared stiff. But I finally managed to rein him back in again and get back. But I've been mad at this guy ever since. I have a picture of me on the horse, incidentally. But we spent weekends in Gatlinburg, Tennessee, which is a very prominent resort area. We camped out in the mountains, and in May of '46, 4 of us took off for the Kentucky Derby, and we in a car, and we got there and couldn't find a vacant hotel. It was completely packed. So we slept in the car, all of us. And I have a picture of sun coming up through the front windshield. But we went to the race, and lucky me, I bet on the winning horse. So I won, must have been about $25 or $30, and we all shared mint juleps, and we had a great time. And we had transportation, which was lucky. Oh, we were in Chattanooga and all over the place. There wasn't very much in the way of technical information that I can give you about what I was doing at K25. It was in a laboratory that was devoted to the chemistry of fluorine. It was run by Dr. Homer Priest, who was a widely known scientist, and we were working on some corrosion reactions. I don't remember my civilian group leader, but the assistant group leader's name was Harvey, what's his last name? Harvey. I'll think of it. But there were a group of us, mostly civilians. Another friend of mine at that time worked in an adjacent lab. His name was Richard Wiswall. And I ran into Dick again, who was at Brookhaven. He was my supervisor at Brookhaven. That was one of the reasons I suppose that I got that job. Okay, well, this was in June of 1946. Things were starting to close down, and I was asked whether I wanted to participate in the bikini test, which was scheduled for that summer, or be discharged. I decided to be discharged. So I went to Fort Bragg, North Carolina, and was discharged in the middle of July of 46. I went home, got married in August, and I had written various letters to universities inquiring whether they had any assistantships. And I got an offer from the University of Wisconsin and from Michigan State University. I applied to Minnesota, but they had completed things. The reason why I applied to these places was because it was so late in the season. I really didn't expect to get an appointment. So I went back to Brooklyn Poly and talked to the head of the department, who was my old pal. And he said, "Look, Billy," he was one of the few people who called me Billy, "I'll give you an assistantship, but apply to these 3 schools. If they don't give you an assistantship, I'll give you an assistantship at Brooklyn Poly." He said, "Get out of New York. Get out of New York and find out what the rest of the country is like." And I've never regretted that information. He was a good friend. So we were married on August 16th, 1946. My assistantship at Wisconsin started day after Labor Day in September. So we packed up what little we had and got on the train and went to Madison. Got off the train with our luggage, standing there on the platform, didn't know a soul in town, had no way of knowing anything about anything, and we managed. So Sally got I got an assistantship in the chemistry department, teaching that first year, and then I got a research assistantship with a former member of the project. He was a chemist, and he was heading up a radiochemistry group, which I joined, and I got a research assistantship with him. And Sally, my wife, got an assistantship in the library school. She had worked for the library system in Brooklyn and had a degree from Brooklyn College in English. And she went in looking for a job, and they offered her an assistantship. So we both had assistantships. I had the GI Bill, and we finally found a 1-room apartment that we lived in for almost all of our stay in Wisconsin. My doctorate degree came in December of 43. And this was a short time. I didn't bother to take a master's degree. I went straight through to the doctorate.
And what year was that?
43.
43.
I'm sorry, 49. 49, not 43. Yes, I entered in September of 46 and got out in December of 49. And I decided that I didn't want to go into industry. I didn't want to go to a university and teach. What was there intermediate between those two? It was a national laboratory where I could do research, where the environment was academic. It was the best of both worlds. So I wrote to Brookhaven, which is on Long Island. And they made me an offer. And the offer was interesting. When uranium from a nuclear reactor was processed to find the U-235, or the uranium in the other kind of piles produced plutonium. You had to be able to separate the two. Why? Because the fission products had very high neutron absorption cross-sections, and they acted as a poison, and the reactor could no longer operate unless these poisons were removed. Poison meaning there was efficient neutron absorbers, and you couldn't get enough neutrons to maintain the multiplication factor. So how do you process this? Well, they had some big plants up at Hanford where they were producing plutonium, and they had enormous chemical processing systems. And what happened there was that they had many wastes. After they've done the processing, they had a lot of chemicals. So they stored them in stainless steel tanks underground. We told them, be careful. Those tanks are still there, and they're still leaking, and they're contaminating half of Washington State. And nothing has been done about that. At Brookhaven, the problem that was handed to me was the ultimate disposal of long-lived fission product wastes. What do you do with them? Well, they were saying you dump them in the ocean. That was discarded. You put them in a rocket and shoot them off out into space. And that was discarded. So the head of my project was a sanitary engineer. Waste disposal. Not exactly his field. So he came to me and said, here's our problem. What do you suggest we do? So it took me a little while. And I said, well, why don't we try separating the uranium from the fission products by selective adsorption? And that's what we worked on. We found a naturally occurring clay that was called an ion exchanger. It had sodium ions in the clay structure, but these were exchangeable with ions in solution outside the clay. So if the fission product ions were exchanged for the sodium in the clay, they would be in the clay itself. So this is what we did. We found that it worked, but it was still exchangeable. So we heated it up. And when the clay is heated, it changes its composition. And because the clay is composed of a series of interconnecting layers with the exchangeable ions located between the layers, these layers would come closer together. And pretty soon they'd bond across this, trapping the fission products, which is what we did. And we heated this material and then carried out year-long tests on the release of the fission products with time. And it turns out that if you plot amount released versus time, the curve looks like this. It starts off high, gets down to practically nothing. And we did this for a number of fission products and demonstrated that the process worked. So we published this information, and it's in the literature. So we had a process that had the starting information, but it needed some work, a lot of work. The Atomic Energy Commission didn't want to push this, and Brookhaven didn't have the funds to be able to fund this any further, and so the project was eliminated. And we still do not have a method for ultimate disposal of these wastes. The best thing that they're doing now is to mix it with a material that will can be melted at low temperature, form a glass, put the glass in drums, and store them in a mountain out in Nevada or Utah. And they've been doing this now for a number of years. And no one has made the decision, this is what we're going to do with all the waste. So all the waste at Hanford need to be treated before they all dissipate into the ground. Problem with these wastes are that they contain a lot of fluorides, they're very highly acidic, and you're going to need a very well thought out method for incorporating the waste into a material that will not release it. Our test, incidentally, on the release of the radioactive materials was using seawater. We assumed the worst condition, that if seawater encountered this heated clay, if there was going to be any release, the seawater would do it, and it was infinitesimal. So the principle was there, the initial tests were done, but was never carried out.
So what did you do after that project was closed? You spend
At Brookhaven. Well, I was in the nuclear engineering department at Brookhaven, and they had a government-sponsored project to design and build a nuclear reactor using a liquid metal as the fuel. You see, the current reactors use solid uranium, which had to be dissolved to extract the U-235 and the fission products and to recover the uranium. That's where all the waste came from. So if you used a liquid metal, you could circulate the liquid metal containing fission products to a chemical processing plant, process the liquid metal to remove the fission products, and then circulate it back to the reactor again. There's no canning problem, no handling problem. It would be very good. So this was the LMFR, the Liquid Metal Fueled Reactor Project, which was the major activity of the nuclear engineering department. And they said, why don't you look into the processing, the chemical processing of the fuel to remove fission products. So that's what I did. Set up a laboratory, and what we did was to contact the liquid metal. Incidentally, the liquid metal was a solution of uranium in bismuth, liquid bismuth, which melts at a fairly low temperature, has a low vapor pressure, and you can operate it over a long temperature range. And it turns out that if you look at the thermodynamics involved, if you use a molten salt, take a material which in our case was a mixture of sodium chloride, potassium chloride, and magnesium chloride, and you melted that together, then at about 500 or 600 degrees Celsius, this is a liquid, which is not miscible with the molten metal. So if somehow you brought the two together and circulated this salt through the metal, the magnesium chloride would react with the fission products and form fission product chlorides, which is soluble in the salt. And so you could remove the salt separately, and you've removed the fission products. This we did. We measured the distribution of fission products between high activity fission products in uranium, which we made, and the molten salt. So we did this on a laboratory scale. This had to be done in a vacuum system in the absence of moisture and air and oxygen. Now let me go back to something that I was referring to. When I was on shift work at SAM labs, we had a lot of time in between readings that we had to take. So I spent that time learning vacuum technique, glass blowing, machine shop operations. We had our own facilities. And I became quite proficient in these areas. I've used these techniques in my entire career. So when it came to handling liquid bismuth in an inert atmosphere, no problem. I knew how to make an inert gas, which was oxygen-free, water-free, and how to measure these things, how to operate inside of a glove box. We were handling fairly large activities, highly radioactive fission products, which we got from Kellex. Kellex in New Jersey was carrying out the processing of uranium products from a reactor to remove U-235. And they had a lot of waste material. We needed some highly active, aged fission products, because the ones that had a short half-life would decay away and aren't a problem. It's the ones with half-lives of the order of months to years that were significant. Kellex had this in New Jersey. So I requisitioned a panel truck from Brookhaven and drove out to New Jersey. In the back of the truck, I had a pig. A pig is a shielded container made of lead. This one was about 1.5 feet in diameter, maybe 2 feet high, which weighed a lot. I put this pig in the back of the panel truck and drove out to New Jersey alone. I had a glass container inside the pig, and they transferred some very highly active solution into that. Put the pig back together again and started back to Brookhaven. At one point, I had to make a sudden stop. The floor of the panel truck was steel. And this, I did not tie down the pig. And I made a sudden stop, and the pig kept going and hit the back of the seat that I was in. Fortunately, it was braced properly, and there wasn't any damage. Nothing got broken. So I drove back to Brookhaven, through the Hudson Tunnel, through downtown Manhattan, through Long Island, with this highly radioactive stuff in the back. Nobody knew about it. They would never have let me do it. So fortunately, I got it back to Brookhaven and used it without any incident. But the Curie at that time was a very high level of activity. They were talking about microcuries and millicuries. Millicurie was substantial radiation. This was many curies in that pig. Lucky.
You know, one of the things that we just got a small grant to write about emigre scientists, Jewish emigre scientists.
Yes.
And I assume you're first generation born here, but can you talk about what it was like on the Manhattan Project? I'm sure you met others who were born.
Yeah, there were
refugees.
many Jewish scientists who had escaped from Nazi Germany, from Belgium, from Norway, from Denmark especially, and they came to this country. There was no problem that I knew of in the way of a reaction towards Jews. The people that we dealt with were highly educated. The only one that I really met, well, okay, let me back off again. The project at Columbia was headed by Harold Urey. And Urey was the Nobel Prize winner who discovered deuterium. And under Urey were a number of other scientists who were equally well known. There was Dunning, who was a physicist who invented the cyclotron, and he had a cyclotron in the basement of Pupin. There was Neer from Minnesota, who invented the mass spectrometer. I'll tell you a little about that. There was E.T. Booth, who was a physicist in many areas. He was very important in the design of the test boxes that we used. I can tell you about that. Willard Libby, who invented the carbon-14 dating system. It was actually invented by his students, but he takes the credit for it. He was head of our group. There was another guy from Johns Hopkins, name of Paul Emmett. Paul Emmett, and he has an equation named after him, the Stephen Brunauer, Paul Emmett, Edward Teller equation on the adsorption of gases on surfaces is a very prominent equation that's used all the time. So Paul Emmett brought some of his students along, and they were working in the same laboratory that I was, the two of them especially, that I knew from Johns Hopkins. I did meet Fermi. I met Fermi at Brookhaven. Brookhaven had apartments for visiting scientists. And I was supposed to move from one house to another. And my other house wasn't complete yet. I had a place to live. So I moved my wife and my youngster. Fermi had the adjacent apartment. So I met him, a very nice guy, very nice. Leo Szilard, I didn't meet him, but a lot of the people on the project would come to Brookhaven to lecture. And I did hear a number of them, and I met some of them. But there was never any inkling of any religious intolerance that I ran into. Now, I can't speak for what happened out in Los Alamos. I don't know if they had any problems there. But there were projects, as you know, all over the country.
What would you like to say as a parting shot about your experience on the Manhattan Project and how it shaped the rest of your life?
I'd say one of the best decisions I ever made was joining the Manhattan Project, because I got all kinds of experience and met all kinds of people, learned all sorts of new things by being on the project. I made a lot of friends who helped later on in my career. Dick Wiswall, who was who worked next door to me at K25, was my supervisor at Brookhaven. After I went off the fission product stabilization thing, I had all kinds of other projects going, and he was a good supervisor. Ray Hughes, who worked in my department at K25, was also at Brookhaven. All these guys come together ultimately. Let's see who else.
Do you have any, another project we're working on is innovations and how
Oh yes.
people were forced to be creative and resourceful?
Oh yes, that was my stock in trade. Uh,
Can you say that?
I worked at Brookhaven for about 10 years and retired as a senior chemist. I felt that I had to get out of Brookhaven. So I applied for a job in California. I knew somebody, I met somebody at a meeting. He worked for Atomics International, which was a laboratory of North American aviation. And it was like a national laboratory. It was completely funded by the Atomic Energy Commission. So what did I work on? I worked on a new kind of reactor. I dreamed up a reactor that instead of molten metal, used molten salt. And I used molten fluorides. No, I'm sorry. Molten phosphates. Oak Ridge was working on a molten fluoride system. After Atomics International, that was taken over by Rockwell. They wanted me to work on some project on diffusion, and I wasn't too happy with that. So there was a friend of mine who was working at Douglas Aircraft on a space-based nuclear power system. How do you cool a space-based system? What do you do with the heat? Well, the only thing you can do with it is radiate it. There's no conduction, no convection. Radiation was the only thing. So if you calculate the amount of surface necessary to dissipate the heat from either a power reactor or a propulsion reactor in space, it's enormous. So what do you do? It turns out that the coolant for that reactor was molten potassium. And they picked molten potassium because it had a low cross-section, neutron absorption cross-section, and it had a very long liquid range and a very low, relatively low, vapor pressure at high temperatures. So you could circulate it between the hot reactor and a heat transfer system that radiated the heat to space and then circulated back into the thing. But what do you contain molten potassium in? It's a very reactive metal. So our job was to measure the solubility of high temperature metals in molten potassium up to, I think it was 1300 degrees Celsius. So that's what I did. There was a guy at Douglas, whom I had known at Brookhaven, who was a metallurgist at Brookhaven, and they needed somebody with some chemical background. So he tried to get me away from the Air Force. I was working for the Air Force at the time. And I finally decided to go. So I took over that laboratory. And we built the equipment for measuring the solubilities of tantalum, zirconium, tungsten, molybdenum, all the high temperature metals. And that wasn't an easy job. So that's another thing. When that project was finished, they needed somebody in nuclear radiation effects. Because out in space, you've got all kinds of radiation. I was in charge of that group. And I wrote a monograph for NASA on the effects of nuclear radiation on materials of interest to NASA. At that time, silicon was the major material for making chips, and they needed something that was more resistant to radiation. So they started working with gallium arsenide. So we looked at the effect of nuclear radiation on gallium arsenide. We irradiated it in a pile and then looked at it spectroscopically. And it turned out that the damage that was produced looked like the spectrum that you'd get for a dispersion of a liquid metal in a non-conductor. Little droplets throughout the material, which affected the infrared transmission spectrum. So we did some work on that. And fortunately, I had a theoretical nuclear physicist working with me, who was a great guy. So I was the experimental end, he was the theoretical end, and we solved the problem. And gallium arsenide was and still is being used because it is highly resistant to some kinds of radiation. Another kind of radiation that was important was electromagnetic pulse. If a nuclear weapon goes off out in space, it produces a lot of radiation, electromagnetic radiation, which knocks out all electronics. So how do you protect against that? So we did experiments using a simulated EMP generator, which was owned by Northrop at the time, and determined what kinds of materials would work and which ones wouldn't work. So we did that. The work on the infrared spectrum, we had to make measurements at liquid nitrogen temperatures and, in a spectroscope. So we had to have a cryostat that cooled the stuff down so that you can get the radiation in, the radiation out. I worked on that. When this was going on, we worked with the Naval Surface Weapons Laboratory in Maryland, Silver Springs, around there. They had invented a metal that they wanted to use to make submarines out of because it was extremely tough, it was corrosion resistant, and it was very strange. This metal they called nitinol, Nitinol, nickel, titanium, NOL, Naval Ordnance Lab. It was an alloy of titanium and nickel. And this alloy had a memory. If you now deformed the material in some way and then heated it back up again, it would return to its original configuration, producing more work than was required to deform it in the first place. Where'd the work come from? From the heat that you put in. So it was a converter of thermal energy to mechanical energy. Now, if you think about that for a while, if you did this on a cyclic process, you'd have a producer of energy. Well, I was working for McDonnell Douglas at the time. We got some funds. We wrote a proposal to the Atomic Energy Commission. We got a contract to build such an engine. It called for a 1 kilowatt engine. And after a while, we put one together. Didn't quite make 1 kilowatt. It made half a kilowatt. And since that time, this metal with a memory has expanded all over industry. Not only that one, but there are other alloys that do similar things. This is a way to move things, make movements. And in the high temperature form, this metal is extremely tough, hard. I just read where they're going to make ball bearings out of it because there's no wear. And it'll take temperatures. And I recently ran into a book that describes a conference on metal with memories and what their applications are. They're used in medicine. It's extremely resistant. I actually have one of those in me. I have a filter in my tube here, which will trap particles of blood clots that are formed elsewhere and prevent them from getting to the brain. And this is made of this metal nitinol. I built engines. I've got one that works. I've written many papers on it. And these are instances where there is a problem involved, and a problem is tossed into your lap, and they say, solve it. And sometimes you need a wide background of experience in all kinds of areas. I'm a physical chemist. I retired from McDonnell Douglas and went to work for the Getty Museum in conservation. I was applying technical information to the conservation of artwork. I worked there for 20 years. I worked on the seismic stabilization of Byzantine churches in Macedonia. How do you modify them so that they'll resist earthquakes? I had a 4-year project to do that. And I won an award from the government of Macedonia on that. So all kinds of things go on. I got some papers that I've written that you might be interested in looking at. But this is not all chemistry.
Well, that's terrific. I'm sure you're going to inspire a lot of kids to go into chemistry.
I've had a lot of people working with me.
Isn't that fun?
A lot of very good people. And my philosophy is you pick good people, you give them a problem, and you leave them alone. You don't second guess them until they come to you with a problem. Then you help them. But that's one type of supervisory philosophy.